Consider a case, a linear uniform array of n isotropic point sources of equal magnitude and spacing. That means to say, we have a n number of antenna elements, they are arranged in linear and uniform manner, then we have to calculate the various parameters. Now, so this is the linear array where we are having n number of elements 1, 2, 3, 4, 5, 6 like this. So, n number of elements are arranged in this, and P is the point where we are measuring the field strength due to all these antenna array elements at this particular point, and this is the axis of the antennas. Now, to calculate the field strength at the point P, we need to calculate the field strength at the point P due to the antenna element A1, due to the element A2, A3, A4, A5, A6 like this. How many number of antenna elements are there? So, for all the elements you have to calculate it here. Then E1 equal to E0 into e to the power of J0. That is, so this is the field strength at this point due to the first antenna element. Then E2 is equal to E0 into e to the power of J psi 1, and E3 is equal to E0 into e to the power of J psi 2. So, like this, for the nth element it is E0 into e to the power j n minus 1 into psi 2, where so this psi 1, psi 2, psi 3 are the progressive phase shift between the signals. Now, once you calculate this one, we have to calculate the total field strength at the point P. The total field strength at the point P is the sum of all these field strength at the point P. Therefore, total field strength is equal to E1 plus E2 plus E3 plus E4 up to En. Then here substitute the values of all E1, E2, E3, E4 like this. Then after substituting, we will get equation, we will call it as equation number 1. Then multiply equation number 1 by e to the power of j psi. Then we will get E total into e to the power of j psi equal to E0 into j phi. So, like this, call it as equation number 2. Now, subtract equation 2 from equation number 1, that is, get the difference between the two equations. Then, when you subtract equation 2 from equation number 1, then E total into e to the power of j psi minus 1 equal to E0 into e to the power of j n psi minus 1. Then E total equal to, now this term will come to the numerator, we will get E0 into e to the power of n psi minus 1 divided by e to the power of I psi. Now, once you get this equation, in order to simplify this equation, rewrite this particular equation in such a way that the equation value remains same. Then, so this n psi, we are writing it as psi by 2, okay, that is e to the power of n psi by 2 into e to the power of n psi by 2 minus of e to the power of minus n psi by 2. Similarly, e to the power of j psi, we are writing it as j psi by 2 e to the power of I psi by 2 into e to the power of I psi by 2. Now, if you closely observe, so this term and this term in the trigonometric form, because you know e to the power of theta minus e to the power of minus theta divided by 2 is sin theta. Similarly, here also it is in the form of a sine form, that is, so this equation, if you compare the trigonometric forms, so this is equal to sin theta and this is also equal to the sin theta. So, therefore, we can write this equation is equal to sin of n psi by 2 and divided by sin of psi by 2 into e to the power of I psi by 2 into n minus 1. And this term you are getting, so because, so this term and this term are there. So, if I take this to the numerator, so then it will be n minus 1 into psi by 2. Once we calculate the total field, then we need to calculate the magnitude of the total field and the phase of the total field. The magnitude of the total field is given by E0 into sin of n psi by 2 divided by sin of psi by 2, and the phase angle of the total field is psi by 2 into n minus 1. Once you calculate, then you have to calculate the peaks. The peaks are obtained if this psi tends to 0. We are getting a total maximum field, so that is equal to E0 into n psi by 2 divided by psi by 2, and so this value is equal to n into E0. What this n into E0 indicating is that n into E0 is the maximum field obtained for the entire array. Mean to say that, so whenever you are measuring the signal strength at a particular point P, then the total field strength is n times of the field strength due to the individual source. Now, as this n goes on increases, that is the number of array element goes on increases, then the total signal strength at the point P goes. The directions in which the peaks are obtained, that is psi equal to 0 or dr cos phi plus delta equal to 0. Then array factor is magnitude of the total field divided by magnitude of the maximum field. So, this is equal to 1 by n sin of n psi by 2 divided by sin of psi by 2, and the peak value of this particular array factor is 1. Then the relative field you have to calculate. The relative field is related to peaks of the individual source. In the antenna array, we are having the individual source elements, and we are calculating the fields of the individual source elements with respect to the maximum radiations what you are getting. That is, relative field is nothing but the relative field is related to the peaks of the individual source, and it is calculated from the equation E equal to E total divided by E0. This is equal to sin of n psi by 2, so divided by sin of psi by 2. Now consider the broadside array. So this is the radiation pattern of the broadside array, where we are having the maximum radiation in 90 degree and 270 degrees, and the minimum radiation around 0 degree and 180 degrees, and this is the main lobe and these are the side lobes. Now we need to calculate the peaks and nulls and other parameters. The peaks are obtained from the equation E equal to sin of n psi by 2 divided by sin of n psi by 2, and the direction of the peaks are obtained when psi equal to 0, or so dr cos phi plus delta is equal to 0. Now if delta equal to 0, that is in this equation, if delta equal to 0, then dr cos phi equal to 0. So therefore phi equal to plus or minus cos inverse of 0. So this is going to give us the values of phi is equal to plus or minus 90 degrees. And the condition for broadside array, delta is equal to 0, hence psi is equal to so dr cos phi. Then side lobes. Now you need to calculate the side lobes. The direction of the side lobes are obtained from the equation sin of n psi by 2. So this is equal to 1. Then n psi by 2 is equal to plus or minus 2k plus 1 into pi by 2. And substitute the equation of psi from equation 8. In the equation 8, we are having the values of psi. So this value you have to substitute at this particular point. So then n by 2 dr cos phi equal to plus or minus 2k plus n into pi by 2. And from this equation we can calculate phi equal to plus or minus cos inverse of plus or minus 1 into 2k plus 1 into pi divided by n into dr. And this equation is going to give us the direction of the side lobes. That is, so what are these side lobes you are having? Then nulls. Nulls is a direction in which the magnitude is 0, and this can be obtained from the equation sin of n psi by 2 equal to 0, or n psi by 2 equal to plus or minus k by 2. Substitute the values of psi from the equation number 8, then n by 2 psi is dr cos phi equal to plus or minus k pi. Then from this equation phi is equal to plus or minus cos inverse of plus or minus 2k divided by n into dr. Once you obtain all these values, you can draw the radiation pattern. Now let us solve one problem on broadside array. A linear uniform array of isotropic antenna satisfy the following conditions or parameters. For this, first we have to consider the peaks, then the nulls and the half power points, all other parameters. First calculate the peaks. To calculate the peaks, psi equal to 0 or dr cos phi plus delta is equal to 0. Since in the given equation delta equal to 0, then I can write phi equal to cos inverse of 0. So this is equal to plus or minus 90 degree and 270 degree. That is, along this angle you are getting the maximum radiations. Then side lobes you can calculate. To calculate the side lobes, equation is phi is equal to cos inverse of 2k plus n into pi divided n into dr. In the given equation, n is given as 4 and dr equal to pi. Therefore, substitute in this equation cos inverse of 2k plus n into pi divided by n into dr, 4 into pi, pi and pi will get cancelled. You will left with phi equal to cos inverse of plus or minus 2k plus 1 divided by 2. In this you are having k, go on substituting the different values of the k and calculate the values of phi. For k equal to 0, in this equation, if you substitute, then phi equal to plus or minus 75 degree and plus or minus 104.5 degrees. And if I substitute k equal to 1, I am going to get these angles. You can increase these values, k equal to 2, 3, 4, 5, 6 like this, but for the simplification purposes, only 2 values are taken. Then you can calculate the nulls. To calculate the nulls, equation which is phi is equal to plus or minus cos inverse of 2k into pi divided n into dr. Now once again n into dr value substitute, then phi equal to cos inverse of plus or minus k divided by 2. In this, go on changing the values of k from 0, 1, 2, 3, 4, 5 like this, but for the simplification purpose, here only 3 values are taken. When k equal to 0, phi equal to 0, k equal to 1, this value is equal to 60 and 120 degrees. When k equal to 3, this value is equal to 0 and 180 degrees. Once you calculate all these values, then you can draw the radiation pattern. What that equation is saying is that you are getting the maximum radiation along 90 degree and 270 degrees. The maximum radiation you are getting along 90 and 270 degrees. Then side lobes you are having at an angle of 41.4 degrees, 138 degrees, 75 degrees, 104 degrees like this. So this is the one where you are getting the side lobes. Okay, so this is another side lobe, and so this is the final radiation pattern where you are having the main lobes and the side lobes. Let us calculate bandwidth between the first nulls, that is BWFN. The basic condition for the Broadside system is delta equal to 0, which results in psi is equal to dr cos phi, and E is equal to sin of n psi divided by 2 divided by sin of psi by 2. So, this is the equation already we have derived. Then the possible nulls are obtained or given by sin of n psi by 2 equal to 0, or n psi by 2 is equal to plus or minus k phi, or phi is equal to cos inverse of plus or minus 2 k pi divided by n into dr. Then the beam width phi 0 can be obtained from phi dash as BWFN is equal to 2 into 90 minus phi, where phi dash is the null adjacent to the main lobe measured above the axis and below 90-degree axis. So, that the meaning of this is that, so this is the angle phi dash what we are having, it is the null adjacent to the main lobe. Now, this is our main lobe and this is the null point we are having because we are not having any radiation here, above the axis and below the 90-degree. So, this is above the axis and below the 90-degree. So, that is whatever this angle we are getting which is adjacent to the main lobe, so that we are calling it as a phi dash. Okay. Then phi dash equal to cos inverse of 2 pi divided by n into dr. Hence, phi 0 is equal to 2 into 90 minus cos inverse of 2 pi divided by n into dr. So, therefore, phi is equal to 2 sin inverse of 2 pi divided by n into dr. Then from this equation, bandwidth between the first null phi is equal to 60 degrees and half power beamwidth is equal to phi 0 divided by 2. So, this is equal to 30 degrees, and peaks of the side lobes are obtained when phi is equal to 41.4 or 138.6. That is, peaks of the side lobes are obtained at an angle of 41.4 and 138.6. Now, psi is equal to dr cos phi. This is equal to pi into cos of 41.4. One of the angle has been taken here. So, this is equal to 135.02, and field strength equal to sin of 4 by 2 into 135.02 divided by sin by 1 by 2 into 135.02. You are getting it as 1.02. So, this is how you can solve the problems.